My name is Roychoudhury, and today I'm going to be talking to you about additive manufacturing in the automotive industry. With the advent of additive manufacturing, the scope of what can be built has increased tremendously. As this field has matured, the cost to purchase additive manufacturing printers has decreased, and has therefore allowed for a lower barrier to entry. This has led to the uptake of additive manufacturing in many industries. Companies have the ability to prototype, test, and iterate on innovative solutions with relative ease. The usability of these tools has also adapted over time and has allowed various levels of engineers and designers to utilize this technology. Automotive manufacturing accounts for a third of the global industry revenue of over $2 trillion. Peripherally, there is a $1.5 trillion parts and accessories manufacturing sector, which sees a high number of competitors due to a larger number of smaller players. To survive and succeed in such an environment, companies are beginning to focus on specific capabilities that they can lead to greater competitiveness. One of these capabilities includes using additive manufacturing, which offers advantages in product innovation and supply chain transformation. Additionally, additive manufacturing can produce components that are not subject to the design restrictions that are characteristic of traditional manufacturing. Over 30 years ago, additive manufacturing found its roots in the automotive industry with the Ford Car Company, purchasing the third ever 3D printer. Since then, additive manufacturing has started to see a higher rate of adoption in the automotive industry. This technology has been used as a source of product innovation and a driver for supply chain transformation. New cars have been coming out quicker and quicker with the ability to now produce lightweight parts in highly customized geometries. Additive manufacturing can be utilized for specialized production of parts. One application of such is through the new production batches of old OEM car parts. As models go out of production, spare parts for these cars become challenging to find. Additive manufacturing has allowed these OEM manufacturers to create limited runs of unique parts. This mitigates the high tooling costs associated with these components and thereby making these parts accessible and, as an added benefit, more affordable. Additionally, PBF is used in creating personalized parts in motorsport. Each driver may have a unique set of requests that optimizes their driving experience that are subject to change. Additive manufacturing allows for these teams to quickly produce these new parts and enhance the driver's experience. Companies like SLM Solutions are leaders in the space of PBF in the automotive industry. These PBF solutions make use of materials such as stainless steel, titanium, aluminum, cobalt chrome, and steel. And these allow companies to diversify the products that they're creating. We have discussed PBF in the past, but I will give you a brief overview of how the process works. Power bed fusion methods use either a laser or electron beam to melt and fuse material powder together. A layer, typically a tenth of a millimeter thick, of material is spread over the build platform. A laser fuses the first layer or first cross-section of the model, and a new layer of powder is then spread across the previous layer using a roller. Further layers or cross-sections are fused and added, and the process repeats until the entire model is created. Loose, unfused powder remains in position but is removed during post-processing. Now, the benefits of using PBF include the fact that these methods are inexpensive, offer the ability to reiteratively prototype, and make use of stronger base materials. In terms of drawbacks, however, this process typically takes some time and has limitations in size and requires high power input. The automotive industry also utilizes the binder jetting additive manufacturing process. This again uses a powder material which instead uses a binder to create these 3D structures. In essence, a powder material is spread over the build platform using a roller. The printhead deposits the binder adhesive on top of the powder where required, and then the build platform is lowered by the model's layer thickness. Another layer of powder is spread over the previous layer, and the object is then formed where the powder is bound to the liquid. Unbound powder remains in position surrounding the object as support material. Binder jetting is a little bit more flexible in the materials that can be used and allow for enhanced material strength with the opportunity to combine multiple materials. Binder jetting is applied mostly in industry due to its set of benefits. The ability to quickly produce parts creates value in integrating the product in the assembly line. Additionally, this modality is low in cost and, as mentioned previously, allows for the use of diverse range of materials. All told, this offers the manufacturers diversity in rapid production of automotive components. Binder jetting does fall short in some respects. For instance, these materials do not have the strongest strength profile and can also, depending on the particular geometry, require some post-processing. This processing includes infiltration or sintering. Looking forward, 3D printing in the automotive industry has a few interesting applications. Most impressive is the ability to fully 3D print cars. Elementary examples of this do exist, and as an understanding of the intricacies of the software improve, the utilization of this technology will increase. Tangentially, costs of additive manufacturing are decreasing, which allows smaller companies to prototype and test their unique concepts. This trend in unique features translates to current manufacturers, as well as with companies like Rolls-Royce, which are currently integrating additive manufacturing techniques in order to highly personalize each of their customer cars. Thank you for your time.